All right, hello geometry. Sorry if my voice is a little odd. My throat's a little scratchy today. But today we are going to be reviewing probability. So in this video, we're just going to go over some of the different things we talked about during our probability unit. So an 8-sided dice is rolled. Find the probability of a different event below. So we talked about and or statements. Those are part of our compound probability. So and means we're looking for the intersection of the two events. So when are both events happening at the exact same time, where the result shows up in both even, for example, the probability of rolling an even number and the probability of rolling a number less than 5. I need to get both those results happening. While or was I wanted either of the two results. So for this, for an and event, all we have to do is think of, okay, what numbers are even and also less than 5. And this is, we're rolling an 8-sided dice. So an 8-sided dice is rolled to find the probability of the different event. So I need to think, what are my numbers that are even and less than 5? So my numbers that are even are 2, 4, 6, 8. Well, the only numbers that are less than 5 are 2 and 4. So I have 2 results out of those 8 possibilities that gives me a number that is less than 5. So that's 2 out of 8, which gives me 0.25 as my decimal. And that would be my probability of even and less than 5. Now, if we're looking at the probability of odd or greater than 5, we'd think about this a little bit differently, because our probability for or, we use our general addition rule, which is the probability of A, plus the probability of event B, minus the probability of A and B. So that's our general addition rule for any or statement. Probability of first event plus probability of second event minus our probability of both events happening. So I need to think probability of A, my first event, is probability of getting an odd number. So what are my odd numbers? Well, on an 8-sided dice, there's 4 even numbers, 4 odd numbers. So we have 4 out of 8 is our probability of getting an odd number. And then I have to think about my probability of event B, my probability of getting a number greater than 5. So what numbers are greater than 5? Well, 6, 7, and 8 are all numbers that are greater than 5. So that's 3 out of 8 is my probability of getting a number greater than 5. And then lastly, I need to subtract the probability of A and B. So my odd numbers and numbers that are greater than 5. So what odd numbers are greater than 5? Well, there's only 7. 7 is our only odd number that's greater than 5. So 1 out of 8. So we'll do 4 out of 8 plus 3 out of 8 minus 1 out of 8 is going to leave us with 6 out of 8, which gives us 0.75. So you have a 75% chance of rolling a number that is odd or a number that's greater than 5 on an 8-sided dice. So those were our and or statements. So and, we had to think of 2 numbers that were the same, or we had to think what numbers fit under both those categories and how many of those results do we have out of our total. While odd, we had to do the probability of the first event plus probability of the second event minus the probability of both events occurring. Oops, sorry, I messed up my thing. And that gave us our or statement. We also talked about mutually exclusive and independent events. So mutually exclusive means that the two events cannot happen at the same time. So if we want to see if these two events are mutually exclusive, we need to check, okay, is it possible for both these events to occur at the same time? So if I was picking a card from a deck of cards, can I pick a card that's from a deck of cards that is an ace, and can I pick a card from a deck of cards that is a diamond at the same time? So can I pick an ace and a diamond at the same time? Yes, yeah, I can easily pick an ace and a diamond at the same time, because I could pick the ace of diamonds is a card that matches under both those possibilities. So that is mutual. That would be non-mutually exclusive because they can happen at the same time. Independent events are 2 events that do not affect each other. So the probability of one event will not change the probability of the other event occurring. So are these 2 events independent? Rolling a 100-sided dice and getting 100 and scoring 100% on your probability assessment. Are these 2 events independent? Well, rolling that dice shouldn't affect your probability assessment at all. Your probability assessment is based off of your knowledge of it, not based off of your dice roll. So I would say these events are independent because they should not affect each other. And so independent, once again, is do they affect each other? Do they change what will the result of one event change the result of the other event? All right, keep going. We talked about frequency charts or two-way frequency tables where we had a table that was split under different groups. It typically had totals on the end. And we could use these groups to find different probabilities. So, for example, we have this group split up to male and females that are for or against building a new mall. So, what is the probability of picking a person and them being for building the new mall? So, what's our probability of picking a person and them being for building a new mall? So, we just have to think, okay, how many people are for building a new mall, which is 140 out of our total number of people, which is 220. So, we're just going to do our probability of being for building the new mall would just be 140 out of 220. Our total out of our total, or our total that are for out of our total number of people entirely. And if we divide that, we get 0.64 if we round up to 2 decimal places. So about 64% of getting someone who's for building the new mall. So what's the probability of randomly picking them and them being against the new mall, given that they're male? So now that we have this given statement, so we have this conditional probability where they're giving us this extra information that they're saying that the person we already know is male. So rather than looking at the entire table, we only need to look through this male row up here. So I need to think, okay, how many people are against given that they're male? So the number of people that are against and male in that row is 48. So my probability of being against building the new mall, given that they're male, we had 48 people who were against a male out of a total of 110 that are male. Because once again, I'm just looking at just the male population for this group because I was given that the person is male. So we'll do 48 divided by 110, and that will give us our results. So 48 divided by 110 is 0.44, and that is our final answer. So once again, conditional probability is just giving us, just sort of narrowing down our results to a single column or a single row, and then finding the probability from that rather than using the entire table. We also talked about conditional probability without using, without having a table. So suppose that 62% of children are given a weekly allowance and 38% of children do household chores to earn their allowance. What is the probability that a child does household chores given that the child gets an allowance? So we know the probability of the way we find conditional probability is the probability of event B given event A. So our conditional probability of B given A, that event B will occur given that we have some information about A, is always equal to the probability of B and A occurring, so the intersection of the two events, divided by the probability of event A, the given event. So it's the probability of both events occurring divided by the given probability occurring. That's always what we're looking for conditional. So I need to think, what's the probability of both these events occurring? So I was given two pieces of information. I was given 62% of children are given a weekly allowance as one piece of information. And I was given 38% of children do household chores to earn their allowance. Those are two pieces of information we were given. So 32% of chores, or 32% of children do their chores to earn their allowance, shows that they're earning an allowance and doing household chores. So that would be falling under both events, doing household chores and earning an allowance. So that's going to be my and statement. So 38% is going to be my numerator. Now my denominator of my fraction, my probability of my just normal event, my given event, was I'm looking for the probability that the given event was the child gets an allowance. So the probability that someone gets an allowance, we had 62% of children get a weekly allowance. So my denominator of my factor is just going to be 62. So I just have to do 38 divided by 62. And that will be my solution, which is 0.61. So 61% of children get or do household chores given that they get an allowance. So most students most children who get an allowance have to do chores for their allowance. So that was conditional probability. So once again, the conditional probability of B given A is always equal to the probability of both events occurring divided by the probability of the given event. So event A and B are independent. The probability of event A is 0.65 and the probability of event B is 0.43. What is the probability of event A occurring given that event B has already happened? So we know that these two events are independent, which means they do not affect each other. So anytime we have independent events, the probability of B given A, the conditional probability of the two events, if the two events are independent, it means they do not affect each other. So the probability of B occurring, given that A has already occurred, is just going to be equal to the probability of B occurring, because A does not affect B at all. It does not change the fact that it's going to occur more likely or less likely or anything at all. It's just going to occur at the same rate that it normally would without A. So in this case, if we're looking for the probability of event A occurring, given that event B has happened, so we're looking for the probability of event A occurring, given that event B has happened, we know the events are independent. We know this is just going to be equal to the probability of event A. It's just equal to our normal probability. So what was our probability of event A? We were given 0.65. So 0.65 is our probability, and we're done. That's all we had to do. If you actually wanted to calculate this, we know that it's the probability of the and statement divided by the or statement, the probability of the and statement divided by the given probability. Well, in order to find the independent, or in order to find the intersection of two independent events, we have to multiply those two probabilities together. So in our numerator of our fraction, it would be 0.65 times 0.43 would be the and of the two events. And then we would have to divide by the given probability, which is event B in this case, which is dividing by 0.43. So we're multiplying by 0.43 and dividing by 0.43, which is just going to cancel itself out. And so you're just going to be left with your 0.65 once again. So that's another way mathematically that this works. But you should always be able to remember that if two events are independent, the conditional probability does not work. It's just the normal probability because they're independent. They don't affect each other at all. The last thing we talked about was tree diagrams. In tree diagrams, we had to sort of draw a picture to help us sort of find these probabilities. And this is when you sort of have multiple events occurring that are affected by each other. So not necessarily independent. So suppose that there are two stoplights between your home and school. You have determined that 70% of the time you were stopped at the first light, and 40% of the time you were stopped at both lights. If you were not stopped at the first stoplight, there was a 50% chance that you were stopped at the second stoplight. Create a tree diagram to help you. So what is the probability that you were not stopped at either stoplight? So I'm going to create this tree diagram. So we're going to start off with some rows. And then from each of those two events, there's two other things that can occur. All right, so the first thing is you have the first stoplight. So the first stoplight, we said you have determined that there's a 70% chance that you were stopped at the first stoplight. So your chance of getting stopped is 70% or 0.70. So that means your chance of not stopping at the first stoplight is going to be, if all of this is out of 100, if 70% chance of stopping, that means you have a 30% chance or 0.30% chance of not stopping. So once you stop at the first stoplight or not stop at the first stoplight, there's always that second stoplight. So you have now as well, we have that second stoplight. So on that second stoplight, we could get stopped or we could get not stopped on the second stoplight. Well, we were told that you have a 70% chance that you were stopped at the first stoplight and a 40% chance that you were stopped at both. So if you're stopped at the first stoplight and then you're stopped at the second stoplight, we said that is a 40% chance. That's 0.40. So that means your chance of not getting stopped at both is going to be 0.60. And then we have to think about this bottom part. If you're not stopped at the first stoplight, what is your probability of stopping and not stopping? Stop at the second and not stop. All right, so if you're stopped at there's a 50% chance that you're stopped at the second. So if you're not stopped at the first stoplight, we said there was a 50% chance of 0.50, which leaves another 50% chance for the last one. All right, so these are all our different probabilities. So we are looking for what is the probability that you are not stopped by either light. That you are not stopped by either light. So our not stopped by either light, that is going to be this row right here. We have to go down this path, and then we have to go down this path. This is our not stopped by either light. So what is the chance of this path happening? Well, we just have to multiply along these rows. So we are going to take our probability of not getting stopped at the first one, which is 0.30. Let me type this out, actually. Sorry. Our probability of not getting stopped at the first one, which is 0.30, times our probability of not getting stopped at the second stoplight, which is 0.50, and we just have to multiply those together. So 0.30 times 0.50 should give me 0.15. So there is a 15% chance that I am not stopped by either stoplight on my way to wherever, on my way from home and school. And so that is how we do our tree diagram. If we had multiple things that we had to go together, so for example, if you're looking at not getting stopped at the second stoplight at all, we would add this row and this row together after multiplying down the rows. But that is our tree diagram. So tree diagrams are a little bit tricky, but creating those pictures can be helpful in order to solve. So that is our probability review. You have a couple other probability review things that you can work on as well. We have the English versus math class event, and then that probability practice. And then your assessment will be the next time that we meet together for class. Let me know if you have any questions. Other than that, have a great rest of your day.